All right, well, welcome to another class of discrete mathematics with Musa and friends. Maybe in the future. So I would like to let you know, keep you updated. So some people were, there was some demand for a reference sheet. We have this formal one, which is mostly complete. There's some stuff from this week that hasn't been placed there yet, but otherwise most of the stuff from exercises to homeworks, almost everything is there, with the exception of relations, which are somewhat new. So hopefully that will be helpful. And the names are the names you've seen in CalcCheck. So that's the benefit of using this. All the names you've seen in CalcCheck, you don't have to go through notebooks looking for the precise name of things. You can just use this handy dandy table of contents and find what you want, right? So hopefully that will be useful. But this is pretty long. This is 10 sections, and one of them has 8 subsections, so it's a bit lengthy to look at. And there's intentional repetition, like quantification. We repeat it for all, some, and it doesn't really need to be repeated so frequently. So on the other side over here, we made a cheat sheet that is a bit more compact. This one this is a total of 3 pages, and this one is up to date. Just finished it before lecture right now. So hopefully it will be helpful to most people. So chapter 3 is this is chapter 3 and 4 right here, squeezed in. Then more of chapter 3 and 4 squeezed into orders and lattices. Quantifiers get only this little tiny corner, not that much on quantification, just the really important stuff you should know. Set theory, as we said, set theory is just packaged up propositional logic. So set theory gets its own little corner. Hopefully we'll get into combinatorics maybe next week. So just put that in there for now. And residuals, as you've seen them in assignment 3, right here. And assignment 4 gets the rest of page 3. The rest of page 3 is assignment 4 and relations. So hopefully that's a lot of fun stuff. If you find an error or you think more things should be added, please let me know. Happy to make these things for you guys. Okay, next. So as mentioned repeatedly, we have these indirect reasoning rules, right? Indirect equality from above, from below, indirect inclusion from above, from below. So hopefully you're very familiar with these, right? And if we're only given, hey, this constant c for any x is at most c precisely when x is at most 5, then by indirect equality we know that x is equal to 5. Okay, so that's what indirect equality from below says. It says 2 things are the same precisely when everything below them, when they share everything from below. Okay, so hopefully you're getting more familiar with this. We talked about residuals before in assignment 3. Residuals are given for the case of meets. Residuals are also known as relative pseudo-complements. Okay, so you get to see another version of division again. Integer division, implication, and then implication for sets is called the pseudo-complement. Okay, and the idea is that division, it internalizes inclusion, right? So when you say x is included in y, that's like saying the identity is included in x under y. Okay, and for meet, the identity of meet is true. So this says true is included in x under y, which is the same thing as just saying x implies y for the Boolean case. Okay, next. So that's the idea here. So when we're given these characterizations, like this one right here, we can use indirect equality to solve for c. Okay, and we find that c equals 5. Here's, just as we have these characterizations for division operators, this division is characterized as the largest piece outside of A still inside B, right? And we would like to calculate for this piece. We want to solve for this piece if possible. All right. Sometimes you can find a definition explicitly. All right. So sometimes you can't. Sometimes you can. Right. And we found a nice little property. So just by unfolding these definitions, right? We know that membership is the same thing as subset. And then when we have subset in hand, we can invoke the characterization of relative pseudo-complement. Now that we have this purely set theoretical formulation in terms of things we know, okay? So remember, the idea is whenever you meet something you don't know, try to bring it back to stuff you do know. And the relative pseudo-complement introduces a new operation that we're not comfortable with, this division, but we're already comfortable with intersections and inclusions. So we change it to be something we're more comfortable with. Okay, so that's the first thing we do here. Actually, let me switch temporarily to a different slide deck for you. This one is a bit too big, I think. Sorry. This one will be better. Oop. Okay. So what we do is we say, hey, you know what? To find a fixed form for A implies B, we first rephrase the membership as inclusion. Okay. Now that we have an inclusion, we can use the characterization of pseudo-complements to get rid of the new thing we don't know into familiar operations we're comfortable with. So now we have an intersection with an inclusion. We know what subset inclusion unfolds as, so we use the definition to turn it into a quantification. Hey, there's one more set thing that we're not comfortable with maybe. Let's use intersection to unfold that away. And now we have all this propositional logic. Except for this membership, let's get rid of that. To be inside a singleton set is the same thing as to be equal to its only member. And now finally, we have a formula that involves no sets besides A and B, right? We've gotten rid of all the set notation, and we're down to just atoms, membership and letters A and B. Okay. So now our goal is to say, all right, how do we how do we simplify this as much as possible? We only want to have an expression involving x on the other side, right? So we have x is inside something, and we want x is inside something else. So let's try to get rid of this y. Right? The first thing to try is to say, hey, when there's an equality, that hints at the 1-point rule. Right? So recall that the 1-point rule just says when you have one option, that one option. Okay, next. So we do trading to allow us to get to the 1-point rule. All right. When we get to the 1-point rule, we apply it, and now we have just an or, and we know how to rephrase this in terms of set theoretic union. Okay. And hopefully this. Somebody says we try. Yep, exactly. 1-point rule is very useful for getting rid of or introducing a quantification. Okay, folks. So the interesting thing here is we read this as A implies B because in the Boolean case, when you say P implies Q, that's the same thing as not P or Q. And surprise, surprise, A implies B is not A or B, the complement of A union B. So we took implication for Booleans. We talked about it. We called that a division. We have integer division. We call those residuals, and now we're back to implication again. So it's all a big circle. Nice stuff. Is there any questions so far? Okay, folks. Please continue asking and making queries as we go along. Okay, folks. So using the above, so this thing is called the relative pseudo-complement, and it's defined by this equation. Okay, so somebody asks what's this A implies B. So A implies B is called a relative pseudo-complement, and it's the largest solution X that makes this equation true. It's the largest piece that lets us have modus ponens for meets in set theory, right? And as you've seen in assignment 3, it's really just another case of division. Okay, so it's a way to divide sets. If you think of intersection as multiplying sets, this arrow triangle is a way to divide sets. Okay, that's all it is. It's a way to divide sets when you think of intersection as multiplication. You're welcome. Please continue asking. Okay. So we can rephrase what we saw. So we have this is equivalent to that. So we can rephrase it yet again, right? We said it's just the complement of a union, but when you unfold a union into an or, and then you realize, hey, this is not something or something else, that's just an implication. And so now you see, hey, X is inside A implies B means if X is inside A, then it has to be inside B. That's pretty neat. And more generally, not just inside of set theory, but in general, if something is included inside the relative pseudo-complement, then whenever it's included in the first one, it's also included in the second one. So this is the idea of internalizing these implications. Right? So that's cool. So let me try to make this even slightly clearer. A implies B is a set. This is just a set. Okay, this is just a set. All right. But when you talk about X is inside A implies X is inside B, that's a propositional formula. Okay, so we can encode these formulae, these proposition formulae, in terms of just values, terms, sets. So that's pretty neat, and that's what we're going with here. Okay. All right. Thank you. So this is pretty neat, and then you can regain complement as dividing by 0 in some sense. Okay, so that's pretty neat. Right. Okay, great. We have yeah. So we have other rules for universal and least elements in the general case for those of you who are interested. But that's pretty neat. So the reason I introduced what we're talking about relative pseudo-complements is just to, again, tie back into assignment 3. Hopefully it's not so people don't forget about it. And we really are going to be using the material in assignment 3 in assignment 4. Okay, so composition, converse, divisions, they do make an appearance. All right, so please do look at them. All right, so we're going to continue talking about relations for the rest of today's lecture, and talking about graphs, and the idea is to get you ready for midterm 5. These things will definitely be there. And we said, hey, you know what, to reduce the amount of quantifiers from propositional logic, we use sets. But then when we want to talk about multiple things, right, instead of just elements, single elements, we have sets of products. But wait, sets of pairs are known as relations. And so that's where we are today. We want to have quantifiers over multiple dummies and quantifiers over multiple variables and give us relations, right? So it's and we'll look at some examples to see how terse and useful this new language is, even though it's an abbreviation for an existing language. Okay, so look at all this right-hand side. All of these lengthy formulae suddenly take on a smaller amount of writing, less symbols to communicate the same thing. Right, so that's pretty neat. Like here's an exists and an and suddenly become a semicolon. A for all and an implication become a division. So these different ones take on different forms. So that's really interesting stuff. Okay, and likewise equivalences become equals, and universal implications become inclusions. So we'll look at a few more examples today. Okay, so again, just to be clear, we're still working in set theory, right? And using these tortoise brackets just means the pair is inside the set R. That's all it means. That's all that's going on. The tortoise brackets means the pair is inside the set. So we're still doing set theory, but now we're talking about set theory involving multiple variables, and This is called relations or relation algebra. Okay. So we've looked at these examples before, and of course the slides are posted on Avenue, so I spent too much time on things we've already seen before. We talked about what a graph is. A graph is a bunch of dots on your paper and lines between them. And then we realized, wait a minute, when there's only a single line between any two dots, and most of that one line, that's just a relation. And so simple graphs are exactly relations, and that's really cool. So studying relations, which is just sets involving multiple variables, is apparently studying simple graph theory. So that's pretty neat, right? That's pretty neat. Graphs may also make an appearance on the midterm, since simple graphs are relations. Okay. So let me just point out this little example for us. So we say a graph consists of a bunch of dots or nodes and lines between them, or edges, at most one line between any two. So here's our dots. They're called 2, 0, 1, 9, 0, 1, 9, and 2. These are the dots I drew in space. And now we're saying there's a line from 2 to 0. So every pair can be thought of as a line. So there's a line from 2 to 0. Great. We're saying there's a line from 9 to 0. So here's a line, and it goes all the way to 0. And then finally, there's a line from 2 to 2. So there's a line all the way from 2 to 2. Okay. And 1 is by itself. It's forever alone. Okay. So relations can be drawn as graphs or as matrices, right? So as discussed in assignment 4. Right? Other places will use this informal notation by putting the relation name in the middle, and we've done that before for less than or equal to. We say x is less than or equal to y, right? So this is a very standard convention. You can also just do set theory convention, and we're going to be using brackets, okay, as shown last time. So somebody's asking about here. So a graph, right? A graph consists of two sets, right? The first one is called the nodes. The second one is called the edges. So here's one set, right? This is just the nodes, right? 2, 0, 1, 9. And then the next set is the edges. And it's a bunch of pairs. Okay, dokes? Good question, Shra. So here's some alternative notation that doesn't work on all stuff. This is experimental. Some people were asking for it. As I showed you last time, just slash open parentheses will give you the tortoise brackets. So hopefully you've looked at it. And of course, just because the tortoise brackets are just an abbreviation for set comprehension for membership, right? Since tortoise brackets are just membership of pairs, all the theorems you've seen before for set theory are now theorems of relation algebra, right? So just repeat them here for you, right? So all of the stuff from before now also applies, okay? And then we're going to introduce some new things. So the new stuff is down here. There's only 1, 2, 3, 4, 5, 6, about 6 or so new things. Really 4 new things, okay? And you've seen these new things before. Identity, you've seen it before. You've seen composition before. In assignment 1, you've seen O+, right? Assignment 4 introduces converse, and you've already seen divisions. So now we're just giving them a new interpretation in terms of sets and relations. Okay, dokes? Does that help? Good. There we go. So the empty set is now the empty relation. It's a relation that takes on, that's never true. It doesn't relate to anything. So if you think of the graphs, right, you draw a bunch of dots, then the empty graph is there's no lines at all. So the empty relation is no lines, okay? The sub-identity relation means, okay, so you have a bunch of dots, and then you say some of them belong to the set B. Then those ones have a line from themselves to themselves. They just have self loops. Okay, just as 2 here has a self loop. Okay, so that's how you can interpret the identity relation on a collection of on a set. Has a bunch of self loops within the larger graph. Okay, folks. The universal relation says, you know what? I'm gonna have all of the product B times C as my dots, and then I'm gonna have a line between any 2 pair. Okay, so there's lines between everything, right? Between all the B's and all the C's. Okay, so you take your graph and you say this side has only B's, this side has only C's, and there's a line between every B and C. Okay, so if you want to think about them this way. And the complement says, okay, wherever there was a line, I'm going to erase it, and I'm going to put and whenever there wasn't a line, I'm going to draw it. Right. So it's like the contrast or inverse of a graph. Okay. Okay, guys. So last time we quickly made it to domain and range. So that was a lot of review. So to be inside the domain of a relation means you consider the graph, and that means you're at the start of a line. Okay. To be in the range means you're at the end of a line. Okay. So for example, Bob is inside the domain of this relation. You can see right here, the domain of the relation contains Bob, because Bob is at the start of this line right here. Okay. And Joe is in the range of this relation, since Joe is at the end of this line. Interestingly, Bob is at the start of this line, but also at the end of this line and that line. So Bob is also in the range, as you can see right here. Okay. So graph theory also comes with all these numerous concepts to talk about. Relations come up with all these concepts to talk about graphs. So it's very helpful. It's a very helpful language. We won't spend too much time on certain parts of it, just because it's such a large field. But I just wanted to let you know. Okay, just want to keep you informed. So here's some example from last time about being called, right? So Helen called somebody. That means in the graph of people calling each other, Helen is at the start of an arrow, and that arrow goes somewhere, and I don't really care. So Helen called somebody. Okay. So the converse, if you have a line from here to there, the converse means flip all the lines, change their direction. Okay. So if I have a line from C to B, if my original graph has a line from B to C, then my converse has a line in the other direction from C to B. It just changes the direction. And this is discussed in assignment 4 in length as being similar to the transpose of a matrix. Right? A matrix has elements at row I, column J. The transpose of the matrix has row J, column I. It flips them around. Okay, and they really are the same. So that's pretty neat. And the composition says, okay, if I have one graph and I have another graph, and they share the nodes, the composition means I can go from I can make one step, one line, and then I can make another line. Okay, so it's like taking a 2-step path. Okay, I take one step via the relation R, and then another step via the relation S. 2 steps. Okay, and if instead of exists you use sum or sigma, and you pretend this is a product, then this is actually relation multiplication. That's really cool. This is matrix multiplication. If you write this as a sum and you treat this as a multiplication, so the matrix R at BC, then the matrix S at CD, being multiply those values and then sum them, you actually do get matrix multiplication. So relations and matrices are so tight, right? So that's pretty neat. Okay. Assignment 4 tries to introduce converse in the lines of transpose or reverse from sequences from 2 weeks ago. as a notion of undoability. So let me just pull that up. So and it also gives hints to things coming up for midterm 5 as usual. So there's a lot of motivation here for it, and it ties all the way back to assignment 1. So what was the piece I want to show? I've since forgotten. It's all right. But the crucial piece is that the transpose of a matrix is its original, right? So some nice pieces, right? Or the transpose changes the arrows, right? If something was the source, now it's the target. Okay, so some little properties about these. And as always, because relations are just sets, we can just prove these using relation extensionality, okay, which is just set extensionality, or we can do using, as always, by doing the relaxed proof style, okay, which is also discussed again in assignment 4. Okay, thanks. All right. So maybe I'll pull up an assignment and we can do some in a little bit. Let me do a few more slides and then maybe you can pull up a CalCheck notebook and do some proofs together. Okay. Or maybe let me do that now actually. All right. Who's interested in seeing an example right now, and who would like to continue going through the slides? Let's have a little bit of a vote. All right, we have one person says example, 2, 3. All right, let's. Okay, so this is the homework 16 notebook 2, which you should have access to by now. Where are we? Let's get to converse, small relations, complement, sub-identity. Oh, there's no converse here. That's unfortunate. Let's introduce converse. Just to show stuff. I will introduce converse. Okay. Playing around. O-A-R-O-N-D. Okay. So let's introduce converse. Declaration. Converse. Do we have the other declarations here? Yeah. Maybe let me open up a different notebook. I'd rather not do full declarations here. All right, more people want to do an example. All right, let's just do an example. All right, so this is not the true type. All right, this is not the true type. This is, oh, that didn't even go through. X. Okay, just to make that happen. All right, so let's write down. There's an axiom 0, which says R converse. So X is inside R converse. Y precisely when Y R X. Let's see that. All right, great. So that's axiom 0. And now we want to prove, we have this theorem we want to prove, theorem 1, which says R converse equals R. Okay. All right, and we're going to say we're using relationality, and that will require us to do a subproof for all x, y, spot x is R converse to y precisely when x is related to y. Okay. Cool. The theorem statement of type cannot be specialized in the proof. Okay. That's because of my fault. This should be to cheat the system, and the system wouldn't have it. System would not have it. So converse takes a set of pairs T1, T2, and returns a set of pairs in the flipped direction. T2, T1. Sorry, T1. Okay, so I tried to cheat, and the system said no, you can't cheat. All right. There we go. Everything good? Does everyone follow what we're trying to do? All right. Are there any questions about what we're trying to do? So we said, you know what, our converse is defined by how it behaves with relations, how it relates elements. And our converse relates X to Y precisely when R relates them in the other way around. Okay, so just like parent of, and then the converse of that is child of, right? So A is a parent of B means B is a child of A, right? The other way around. And we're saying if you flip the flip, you get back where you started. Okay. So we have it for any, right? X comma Y, right? So for any X, okay. Gotta get rid of that question mark. Okay. Okay. So all the traditional relaxed proof style we've encountered before still applies. And so now we're at a calculational proof. Our converse, Y. All right, who wants to tell me what I'm doing here in the first step? Does anybody want to say what's going on in the first step? Axiom 0, exactly. The definition of converse, which we said is just 0. Excellent. And what do we do here next? What is screaming to be invoked? How do you simplify? All right. We started with the complicated side, and now we're simplifying. Okay. Exactly. Use 0 again, which says X, R, Y, and we call it 0, and we're good to go. Look at all that delicious green. All right, delicious green. So this theorem is sometimes called like this. Okay. So sometimes you might see silly theorems like that. You might see some silly theorems like this, or like that. All right. All right. So some silly theorem names. Just trying to have fun with the class, emoji style and whatnot, old school. Okay, next. Are there any other questions or concerns before we move on? So in a similar fashion, we can prove isotonicity of converse. Okay. We just invoke definition of relation inclusion. We apply the definition of converse twice to flip these guys and flip those guys. Okay. Then we just change the order of the dummies, X, Y, Y, X, and then invoke relation inclusion again. Not a big deal. I'm glad you love the emojis. So in assignment 4, I let you choose. You can use these names or the other ones. I think. I don't remember. Yeah. So here's some other silly names if you like. Looks like someone closing their eyes with a big nose. I don't know. Just trying to make your life a little bit fun. I hope you enjoy. So earlier I said composition is taking a two-step path. So what if you say someone is the parent of someone who is the parent of someone else? All right, being the parent of someone who is a parent themselves means you're a grandparent. Okay, so a lot of family relationships can actually be defined really nicely using composition. For example, to be an uncle means to be the brother of a parent. Okay, So to be an aunt means to be the sister of a parent. Okay, so a lot of family relationships really easily are expressed using relation notation. Okay. If we say to be siblings, for example, means so for example, I am the child of someone who happens to be the parent of someone else. Okay, that's what we say when we say it's a sibling, right? So I am a child of someone named C who happens to be the parent of someone named D. Okay, so that's what it means to be a parent. I am the child of someone who happens to be the parent of you. So you and I have the same parent, so we're siblings. But what if you and I are actually the same person? Then that doesn't make sense for us to be siblings. So we're going to say we have a common parent, but we're different people. Okay, so we have a common parent, but we're different people. Right, so we want to subtract out all the cases of x comma x for people, because they should not be related to each other. Right, like for example, Bob is related to himself. Bob should not be his own sibling. Right. So, any okay questions? Okay, good. And again, by treating things as matrices, the identity is really the identity matrix with ones along the diagonal and zeros everywhere else. Right here, the identity matrix. Right. The diagonal has relationships. Everywhere else is zeros, no relationships. So these identities really are the identity matrix. And what we're saying is we're saying, hey, form this relationship, then drop everything on the diagonal. Okay, so notice here's some stuff on the diagonal, right? Bob is related to Bob right here. Okay, right here, and also in the diagonal. But then when we take this matrix and throw away the diagonal part, we end up with this matrix. So that's pretty neat. So again, multiple ways to think of relations as either matrices, as graphs, as relationships, right? So multiple ways. So really neat. I'm not going to spend too much time on this next slide. Just wanted to leave it in there so you could use it yourself. Some of these expressions get really involved, and the nice thing is with relation algebra, they're very easy. So if you think of C as called and B as brother of, this one just says Aus called someone who happened to be the brother of Jun, right? And that almost nicely reads right here. Okay. This one is a bit more involved, right? So Aus did not call someone who happened to be not a brother of Jun, right? Not that hard to read. Aus didn't call someone who was not a brother of Jun. That is to say, everyone called Aus is a brother of Jun, right? So, and the reason for the translation is this exists, right? So if you recall from a moment ago, we said composition gives us a way to talk about exists, okay? And this is negation, and so Aus did not call someone who is not the brother of Jun. Aus didn't call someone who's not the brother of Jun. Or by De Morgan, that's the same thing as saying everyone Aus called is a brother of Jun. Okay. So I was hoping to go a bit fast, but I left that in there. So here's more for you to practice. So hopefully you'll find out what they mean or what they denote, and that will get you to be more comfortable with these operations for relations. Okay, and here's this one is obvious. For any people x, y, z, if x called z, then there is somebody whom x called, right, namely z, right, and who was called by somebody, namely x, who called z, i.e. call is contained in call times call converse times call, right? So sometimes these really long expressions in English can take on really terse formulae. So that's really nice. This one is hard to write in propositional logic. Obama called everyone indirectly or indirectly via at most two intermediaries. It's a bit hard to formalize because there's a lot of quantifiers. each composition is a quantifier right here, right? And when there's multiple quantifiers, that's multiple existential quantifiers. So either called directly or via one intermediary person, so there exists one intermediary, or there exists two. So this is a really long formula. So it really helps to practice these and to be comfortable with using composition to hide the existential quantifiers. Okay. So this translation between relational algebra and propositional logic is also in the cheat sheet with some stuff that we'll get to later on in the class. Okay. So properties of associativity and identity, which you've seen from the very beginning, from assignment 1. Almost all the nice operators have these properties. And likewise, composition has this property because and is associative itself and has a distributivity law over existence. And identity, this is just the 1-point rule, right? So here's an equality right here, and then there's a quantifier. And whenever you have a quantifier and an equality, you 1-point rule to get rid of that quantifier. Okay. And identity is just two things are being equal. That's all. All right. So it's the equality relationship. All right. So that's what identity is. Okay. Please continue to ask questions. I am looking on multiple platforms just to make sure I'm not talking to the void. So sometimes you'll see these relations also maybe next term or next year at least when you get to these diagrams for automata, right? So for example, I'm walking from here to the station, and then when I get to the station, I can either take the bus. I can get home by taking the bus, or I can get home by taking the train. I have two different ways. That's the same thing as saying, oh, okay, let's start off, let's walk to the station, and then we can take the bus, or let's walk to the station, and then we can take the train, right? So it's just a normal distributivity rule you've seen before, right? So I just want to, but notice how the formulae is so long, right? This one gets even longer. Let me go back to my beautiful squares. All right. So it's a really long formula, but it's really short to express in this language because all the quantifiers are hidden. Right. This equality gives us the for all, right? Right here because of extensionality. Equalities give us for alls, and each existence comes from these compositions. So here's one existence on that side, and two existence on this side. Okay, and the ors come from the unions. Okay, so but this is very hard to wrap your head around. What's going on here? Oh, I see. This right here is an or. Okay, and this is an and distributes over or, and distributes over or. Okay, that's pretty neat. Right? You unfold all these scary definitions. Right? You unfold the left-hand side to turn it into this piece. Then you're like, wait a minute. I have an and right here, and this part is an or, and I know and distributes over or, so I say this and that part, or this and the other part. Okay, really nice stuff. And these properties of conjunction and disjunction are summarized really tersely in the 3-page cheat sheet, but more fully in the online one, right? If you're interested. So that's a lot of theorems to keep track of. This much more terse, right? Stuff that you really want to know in this PDF for a quick lookup, but stuff you will or have encountered in the HTML. Okay, ducks. So we talked about these matrices, and so let's look at a few more, and they're really neat. So reflexive means there are self loops when you think of a relation as a graph. But reflexive means you have the whole diagonal. Okay, so for example, this relation is reflexive because the diagonal is there. Okay, because ID means x equals y, and so if x equals y, then x and y are related by r. So that's the diagonal. Okay, so that's pretty neat. Irreflexive means you do not have anything on the diagonal. So this relation is irreflexive, right? Or if you think of it as graphs, irreflexive means there are no self-loops. No self-loops are allowed. Okay. Symmetric, this is just a symmetric matrix you've encountered in linear algebra. Symmetric just means symmetric matrix. It means everything above the diagonal is the same as everything below the diagonal, right? So you only need to remember half the matrix. Okay. Antisymmetric means, hey, if I mirror across the diagonal, then these things must be the same. Right? What does that mean? So I'll let you think about that one a bit more. Asymmetric means I can never have both across the diagonal, right? So lots of fun stuff. This one's pretty cool, so we'll get to that one in a moment. So you've seen these names before. What's an order, right? An order is a reflexive, transitive, mutually inclusive relation, and using these new definitions, it's the same thing. It's a reflexive, transitive, antisymmetric relation. Okay, and recall, antisymmetric and mutual inclusion are the same when you have access to reflexivity. Okay, as you've proven in assignment 2. Okay. And an equivalence relation is when you have reflexive, transitive, and symmetric. An equivalence relation gives you a notion of similarity. So orders give you a notion of approximation, right, or at most, or inclusion. Equivalence relations give you a notion of similarity. Okay, folks. So and idempotent just means if I multiply it by itself, I'm back where I started. There's nothing new. And transitive means if I take a two-step path, well, there's actually an efficient one-step path directly. I don't have to do 2 steps. I can just do 1 step directly. Okay, when you think of it in terms of graphs. Okay, so some things are easier to think of in terms of matrices. Other things are easier to think of in terms of graphs. So it helps to have both ways to view relations. Okay, and the cool thing is we have these 2 ways to view relations, but relations are a way to view abstract division, right? We can view abstract division as relations, but we can also view abstract division as integer division or a Boolean implication. So multiple ways to see the same thing. Really nice stuff. Okay. Here's a cool property about, in order to accommodate the feedback we got from you guys about making assignments, they're too long. Assignment 4 is, most of it is just example proofs, definitions, and fill in the blanks. There's a lot of that. And then we leave a bunch of them empty for you. And it builds on the ideas from assignment 3 as well. Okay. So a theorem like this is mentioned in assignment 4 and assignment 3 without asking you to prove it. I'll just mention it so you don't have to do it. But if a relation has a property, then its converse also has that property. That's pretty neat, right? So, for example, if it's reflexive, that is, every graph has a self loop, or the matrix has the diagonal. Then when you flip the matrix, the diagonal is still there. And if you have your dots with lines everywhere in the graph, and there's self loops, well, a self loop, if you change the direction, it's still a self loop. So reflexivity or self loops are preserved under change of direction. So that's pretty neat. Okay, and the proofs are pretty simple. This one's very cute. Reflexive transitive gives you idempotent, right? So equivalence relations are idempotent, right? If A is equal to B and B is equal to C, then A is equal to C, right? So R times R is contained in R is the transitive part, and then to go the other way around is the proof right here. R is contained in just by the identity, and I know by transitivity, ID is contained in R. So R is contained in R. So these are just simple little proofs. and you're going to see some proofs like this in assignment 4 with more involved names such as univalent, total, mapping, iso, right? And then you're going to prove some similar theorems between them. Okay, so just wanted to show you that. I'm almost out of time, but I just wanted to remind you it's just relation. Relations can be just thought of as just graphs or just matrices, and then composition can be thought of as reachability. So I'm out of time, so I'll just stop here, and hopefully we'll continue this Thursday. And I hope you had a lot of fun. And I'm here to answer questions afterwards if you like. Okay, and please, try to do the assignments and ask for help. And all the best. Yeah.